Hi, everybody. Welcome to the second talk of today. So our next speaker is Kindler, and he's going to talk about small set expansion for the short code graph. So take it away, Guy.
So hypercontractivity or small set expansion. So basically the short code graph so this is small set expander for global sets. And it's a mouthful, so I'll just call it sausage for now. So the short code graph is a sausage. And here is like the gist of what, whole story. So some of the initial motivation at least came from the problem of satisfying a constraint graph. So it's related to computer science. That's what I'm trying to say. You have like a graph, and each vertex can be assigned an element of some finite subset, and the edges are constrained, saying which assignment to one variable and which assignment to the other variables are good. We're good together, and it's known, this is the PCP theorem, that even if you can satisfy all the constraints, satisfying more than delta is NP hard. This is well known. And in O2, Subash conjectured that even if the constraints are one-to-one, I won't describe what it is, then still, if you can satisfy almost all the constraints, still satisfying just delta of them is NP hard. That's a conjecture. He also conjectured something a little weaker, which is that if the constraints are 2-to-2, then still it's NP hard to satisfy even a delta fraction when you can actually satisfy everything. And then there's a long list of papers that eventually resulted in this sort of proof of the 2-to-2 conjecture, except that instead of 1, it's 1 minus delta. So that's a proof of the 2-to-2 conjecture, and this is Kot, Mincer, Safra. The decays are Dinur and Kindler, and this is Barak, Kotari, and Steurer. And the current result is that we take the last two results here, and we somehow prove it again, but in a more generalized, streamlined, shortened, and conceptual manner. So so that was the short version. A little bit more detail, there is something called the Grassmann test. It's a consistency test of a code, and the previous result showed the 2-to-2 conjecture, assuming that this Grassmann test works. And it turns out that for the test to work, it's obviously required that the Grassmann graph is a sausage, whatever that means, I'll say it later. And then we managed to prove a weak version, saying it's some sort of a weak sausage. And then Barak, Kotari, and Steurer proved that actually, if we prove that this graph is a sausage, then it's also sound, and therefore you get the 2-to-2 conjecture, and then Kot and Mincer and Safra proved this, that it's a sausage. So this proved the 2-to-2 conjecture. We prove that the short code graph is a sausage, and conveniently, Barak, Kotari, and Steurer proved that if the short code graph is a sausage, then also the Grassmann graph is a sausage, and therefore the Grassmann test is sound, and therefore 2-to-2 is again proved.
It's equivalent.
Yeah, it's equivalent. Okay. So SSE, it's the beginning of sausage. So what does it mean to be an SSE? So we have a graph. I'll say a graph, but it's actually a family of graphs. And it's an SSE if for every small set, so say the size of S compared to the number of vertices is less than delta, then if you start in a random vertex in S and go on a random edge going out of it, then with probability tending to 1, you go outside of S. So that's a small set expansion. And one very good example of a small set expander is the cube with the graph of the noisy cube. So the vertex set is just 0, 1 to the n, and the edge, it's a weighted graph, so there's a distribution over edges, which goes by picking a random x, and then picking a y such that the ith coordinate of y is the ith coordinate of x with probability rho, but otherwise it's just random. Yeah, so this is the noisy cube, and here's a theorem which says the rho noisy cube is a small set expander. And this follows easily from results of Bonami and also from results of Gross and Beckner. And it's very useful, this fact that the small set expansion of the cube, it was used in KKL, Kankala, and Linear. I won't say all the names. So it was used for collective coin flipping, for showing that low influence functions are juntas. It was used for vertex cover hardness, and for showing that the majority is the stablest global function, and this resulted in max cut hardness and various other things. It's very useful also in combinatorics, not just computer science. Yeah, so that's an important thing. But you don't always have an SSE. So here is something that is not an SSE, not a small set expander, the noisy mesh. What is the noisy mesh? It's very similar to the cube, except instead of 0, 1 to the n, you have 0, 1, 2, 3 up to q to the n. And we think of q as something that grows asymptotically with n. The edge distribution is similar. You pick x randomly if you want to pick a random edge, and then you pick y to be xi initial coordinate with probability rho, and otherwise you just re-randomize it to pick another random number between 0 and q. So the rho noisy mesh is not a small set expander, and here is an example of a small set that does not expand. This is a dictatorship, so just take all the elements in the cube whose ith, maybe, I don't know, 7th coordinate is 17. First of all, it's small, so I could define something similar in the cube, but then it would be, so all elements so that the 7th coordinate is 0, but that would be half the elements in the cube. That's not small. In the noisy mesh, it is small because 17 is just one out of many options. Yeah, so its relative size is 1 over q, but probability of leaving S if we start from S is smaller than 1 over 1 minus rho, because with probability rho, we don't change xi. And so we stay in the set when we go on a random edge. Yeah, okay, so dictatorships such as this are not expanding, but, and you can generalize to juntas, which are determined not just one coordinate, but by several, that they do not expand, but they are local. In the sense that they are defined by looking at a small set of coordinates. So we can discuss non-local, or as it is called, unfortunately, global sets and functions. So what is a global set? So here's a function. Okay, I was talking about sets before, but a function is just, think of it as an indicator of a set. Its 2-norm is just the expectation of the square of the value of the function. And yeah, and we need to talk about restrictions. So the restriction of f on the coordinates of t to an assignment y, it's the function that on x gives f of xy. It's very natural definition here. And the set is d epsilon global if when you restrict d coordinates of f to something, to some fixed value, then the norm is still small. The norm, the 2-norm squared is still less than epsilon. And yeah, and this kills the example from the previous slide, because dictatorships, even if you fix one coordinate to 17, then the norm of what you get is 1, because the indicator of the dictatorship will always be 1 on this restriction. So restrictions, so functions which are small cannot be dictators, and it turns out that once you only restrict to functions that are global, that look like this, then the noisy mesh is a small set expander. So it is a small set expander for global sets, so sausage. So this was proved initially by Kivash, Long, Noam Lifshitz, and Dor. So we have this sausage property for noisy mesh. And among other things, we also reprove it, maybe with slightly worse parameters, but with the same approach, with the same scheme. And also we prove it for the degree 2 short-code graph, which is what gives the 2-2-2 thing. Okay, let's talk about the short-code graph. I guess not everyone knows it. Okay, so I need vertices and edges. The vertices are the linear functions between f2 to the n to f2 to the m for some n and m that I think of as kind of large. We actually, everything works for fq to the n and fq to the m, but we'll stick with 2. And instead of linear functions, you can just think of the collection of matrices. And then an edge is between 2 matrices if the rank of the difference between the 2 matrices is 1. So we look at matrix rank. And again, this graph is not a small set expander because of dictatorships, except that here we will need to redefine what a dictatorship is. So a dictatorship, one option is to look at the set of all matrices that move a vector v exactly to the vector w. So that's a dictatorship, maybe call it right dictatorship. You can think of a left dictatorship, all matrices that if you multiply by w from the left, you get v. So both of these are dictatorships. And what is the probability of escaping a dictatorship? So if you start from maybe S, and then you look at a neighbor of A. So B is obtained from A by adding a matrix of rank 1. Then the probability that that B also satisfies this dictatorship condition is the probability. Okay, so I take A and I add a rank 1 matrix, which is just a product between 2 vectors. So the probability that A plus this rank 1 matrix times V equals A is just the probability that, sorry? Yeah, should be W, that's true. Yeah, I mean, so A times V is W, so this needs to be 0. And among other things, if this times V is 0, then you're done. And the probability that this times V is 0 is 1/2. Okay, so the escape probability is only 1/2, even though it's a pretty small set. So these are dictators, and they are a problem. But again, we show that for global sets, not dictatorships, this expands. Okay, so again, what are restrictions? Just like before, or similar to before, a de-restriction is a restriction to a set that is defined as an intersection of dictatorships, either left or right. So a de-restriction is a restriction to dictatorships. And so once you have that, you have the definition of a d epsilon global function, and we want to prove that such functions expand, or such functions that are indicators of sets expand. Okay, so here is a more quantitative version. So yeah, if you want, if you want to get 1 minus 2 to the minus r expansion, you need r and 2 to the minus r squared parameters of globality. And r can be whatever you want. So this is what we proved, but what we actually prove is a hypercontractive estimate or a norm comparison estimate that says that if a function over this graph is the delta global, then its 4 norm is upper bounded basically by its 2 norm. Delta is the parameter of the globalness, and this is, think of it as a large constant. So, but this is not for the original function, it's only for its d degree part. But that turns out to be enough. Yeah, so you can think of it, you can call this estimate also a Bonami lemma, because Bonami proved something very similar for the Boolean cube. And I need to tell you what a degree D function is, and one way of saying it fast is that it's a linear combination of D, it should be dictatorships. So a linear combination of products of the dictatorships. Yeah, okay. And if you project F on this space, then this is F smaller equal D. Okay, and some few words on how the proof goes before we go to the board. We prove something that looks like this. This is rubbish. It doesn't mean anything. So, but it's somehow. But this is the gist of it. So we want to bound the 4 norm by the 2 norm, and what we actually do is bound the 4 norm by the 2 norm plus a lot of extra stuff. At least this is the first step. And the point is, and there are 2 points about the extra stuff. First of all, these are Laplacians, whatever this means. And their property is that, first of all, well, they are not, if F is of degree D, then these Laplacians, they are not exactly of degree D, but they can, their 4 norm can be bounded by the functions of degree that is strictly smaller than D. So you can sort of apply this again by recursion and really get a bound on the 4 norm of F. And when you look at these smaller degree functions, these smaller degree functions are somehow related to the restrictions of F. So if F is global, then you get these norms of functions that are related to the restrictions of F, and therefore their norm is also small, and therefore you manage to prove something. Right, okay. And to prove it, first you have to define all these Laplacians and influences and derivatives, everything that appears on the board here. And this turns out to be very easy for the noisy cube, less easy, but still possible for the short code graph. Okay, so that's the end of the PowerPoint part. How do I? This? Okay. Yeah, so this proof, this talk, I think will remind you of a lot of past talks from this week and maybe also some weeks before. But yeah, I'll still say a little bit about how these norm comparisons relate to expansion. So you have a graph G and you want to say that it is a small set expander, maybe for maybe for global sets, or maybe just in general. How is this related to norms? So here is a general scheme. Okay, there is a vertex set, and there is a subset S, which is small, and a function f, which is the indicator of S. We want to say something about the probability of escaping S. So it's like we want to show that if you take a random edge, if you take a random x in V, and then a random y that is a neighbor of x in the graph, then the probability that both f of x is 1, so both x is in S and y is in S, that is, this is much smaller than the size of S, which is the 2 norm of f squared. Right, so this is what we want. Okay, and now another way to write it is as the expectation over x in V. And instead of y taking a random neighbor of x and calling it y, I'll write it as f of x times tg of f evaluated at x, and tg of f evaluated at x is just the expectation over neighbors of x of f of y. This is the graph noise operator, which we've seen many variants of already. Right, so this is just a different way of writing the same thing, and this is the inner product between f and tg of f. Okay, and I want to connect all this to norms of low degree parts of f. So I need to define these degrees. So the next step is to write f as a sum of parts of different degrees. I goes from 0 to however is appropriate. And this is f equals I is the pure I degree part of f, and the way that it is defined, it depends on the graph that you are working with, and the idea is that you define these degrees in a way that tg, okay, let's think of f as a sum of the low degree part, just all the sum over all the i's up to d, plus the high degree part. And the idea is that these are, or the space of at most d degree functions is an eigenspace. Sorry, it's not an eigenspace. It's a, what do you call a space that remains invariant? Yeah, it's an invariant space of Tg, and same for the space of functions of degree greater than d. And if you define the degrees correctly, then Tg just kills the parts that are of high degree. So this is going to be much smaller than the norm of f. And so here you have f inner product Tg of the high degree part plus F inner product with TG of the low degree part. And this is basically 0 because TG kills the high degree parts. And this you have to deal with. And similarly to what Noah mentioned in his talk, TG of the small part it doesn't do much to the small part. It's basically the same thing. And therefore, here comes the norm estimation. So now we want to bound this part. And this comes in handy if you can prove it. If you can prove that the phonome of this thing is bounded by some constant, maybe depends on D, times delta, in case we are talking about global functions, times the 2 norm squared. If you have, then you can just, okay, intuitively, it just means that the support of this function is sort of spread, because if it has a really tiny support and gets really high values there, then the phonome will be much higher than the 2 norm. And if the support is spread, then when you inner product it with F, remember F is an indicator of a tiny set, then you'll get something very small. Okay, so this is the intuition. Technically, the easiest way to do it is by doing a Helder. So this is smaller than F smaller than D phonome times. Okay, I forgot about the TG here, right? So this is F smaller than D phonome times F maybe 4/3 norm. And then the 4 norm can be bounded by the 2 norm. And if you work with it right, you get a bound showing that this is much smaller than the 2 norm of the original F. Okay, so that's the motivation for proving bounds of this sort.
TG is not self-adjoint?
TG is self-adjoint, yeah.
So why can't you move it to the other side and then replace F with also with F less than D on the left side? And
I could do many things. It's
but then you just get the L2 norm of F less than D, right? You don't need to go to L2.
Yeah, but I mean, I could.
You want this to get one?
Yeah, I could. I mean, this inner product, even without the TG, it's the same if I put F smaller or equal to D here, because the different degrees are orthogonal. But somehow I gain because I take a norm of F that is not the 2 norm, it's smaller than the 2 norm. I lose because I put the 4 norm here, which is larger, but then I gain again because I have an upper bound of the 4 norm using the 2 norm. So I need to go up to the 4 norm in order to gain something. I mean, this is one of the things that you just have to do by yourself. Okay, so yeah, so this is our goal, proving bounds of this form, Bonami-type bounds. Maybe I'll erase some of this stuff. Right, so for the noisy Boolean cube, we have a Bonami-type bound. It was proven by Bonami, and it says that the 4 norm is smaller than something to the D times the 2 norm if the degree of f is at most d. Yeah.
The inequality as you written it, it's not invariant under scaling, right?
Well, yeah, I needed this. It is because delta is too homogeneous of degree 2, and this is also homogeneous of degree 2. So because delta is a bound on the 2 norm squared of the restrictions of f. So it's fine, but I agree that it's confusing. Okay, yeah, so for the Boolean cube, we have it for the shortcode graph. Yeah, what happens with the shortcode graph? We are talking about functions from the set of matrices F2. Yeah, functions from the set of matrices to R. How can you write such a function? You can write it as sum of f hat s times chi s. Okay. This you can do for functions over the Boolean cube, right? Chi s is just the product of the s coordinates of x, if you think of x as plus minus 1 valued. But matrices over F2 are also just weird vectors of length m times n, just written in a weird way. So you could also write that for S that is a subset of m times n. Right, and then we want a similar result. Why don't we already have it? What? Yeah, okay, so the point is, and this is why I had to do the intro about these degree things. The degrees have to work well with TG, and TG is different here, and so the degrees are different. So here the degree of a character in the Boolean cube is just the size of S. But here, if we want it to work well with the noise operator, the noise operator corresponds to the rank of matrices. So the degree of a character is actually the rank of S when seen as a 0-1 matrix. And this is why this doesn't give a Bonami bound immediately. Okay, and I doubt that I will go back to the shortcode again. I just wanted you to know what the degree is for the shortcode. So now, yeah, once you have a degree of a character, then you can take this sum and bunch it up according to degrees. But let's talk about the noisy mesh. For the noisy mesh, yeah, we have f from q to the n to r. How do you bunch it up to degrees? Well, you can write f as the sum. This is the Efronstein decomposition. So you can write f as a sum of things that I denote f equals s for all subsets of n. And these things are all orthogonal. And f equals s depends only on s. But also it's orthogonal to anything that depends on a subset of the coordinates of s. And that actually defines this, and then the degree of this f at s thing is just the size of s. And then the claim is that we want to prove, and then to use somehow recursion to get a Bonami-type lemma. The claim is that f 4 norm to the 4, this is for d degree, actually, yeah, so sorry, yeah, for d degree function, it holds that its 4 norm is bounded by some constant times its 2 norm to the 4th power plus, so this is the straight up cube Bonami part, Boolean cube, plus all the rest, which is some, 4D S, Laplacian S of F, also 4 norm to the 4 power, going over all S's, all non-empty S's. Yeah, that's how the markers get here, but then they return here in the next talk. Okay. Yeah, it's still the 4 norm to the 4th power, but the idea is that this can be somehow represented by lower degree functions, and then if you assume by induction that you have these 4 lower degree functions, for functions of degree smaller than d, you can apply again. I didn't define the Laplacian, so for now it's just a thing. And I think my next, so the next step is to define Laplacians and the derivatives. But this was sort of general. This is the scheme, but for the scheme to work, I need to define what Laplacians are for my particular graph. This is 9 to the d because there's, 9, yeah. Okay, there will be no Q anymore. Okay, so what are these Laplacians? The S Laplacian of F is just the sum of all elements of the F-Stein decomposition of F for T's that contain S. And there is another thing that I said the name of, but I didn't actually write on the board. There is something called the derivative of F. So a derivative has S, but also has X. And this is a function of Y. So X is actually in, okay, now there is a Q. This is Q to the S. So it's a bunch of coordinates. It's an assignment for the coordinates of S. And the derivative of S at X evaluated for F. Okay, whatever is here in the board, it's defined by the Laplacian S of F, but evaluated at X times Y. So it's the restriction of the Laplacian to X. And the point is that once you took the Laplacian, it only contains FTs with T's that have elements from S, actually have all the elements from S. And now if you fix coordinates from S, then each such element has a lot of its coordinates fixed, and therefore it becomes something of a much lower degree. So that's the idea. Right, and the inspiration from all these definitions come from the Boolean cube, where these are actually derivatives. Okay. Right, so you could write, yeah, so when I had before, maybe it's still on the board, you have the 4 norm squared of the Laplacian. It's actually just the expectation over x chosen randomly from an assignment to the s coordinates of the 4 norm squared of the derivative of f. And these things are already of a smaller degree, and so you can recurse over these.
Telling us the proof of the claim, or?
Okay, so for now, I'm just telling you how once you get the claim, you could recurse, right? Because at least in general, yeah, you have this Laplacian, and then you write it as an expectation of 4 norms of derivatives, and these are of smaller degree, and you assume that for these you already proved something. Yeah.
Rather than on n. So it's the induction on the degree rather than on n, which is maybe more standards.
The induction is on the degree of the function.
On the degree of the function, yeah. Yeah, the induction is on the degree of the function. So these are functions of smaller degree, and so for them, you can apply the inductive hypothesis, and
Is it clear why the degree of the derivative is smaller than the function, like the way you've explained it?
well, f equals t is a function that depends on the coordinates of t.
Okay.
And okay, but t has to be of size at most d, because f was a function of degree at most d. So t is of size at most d, and then you fix some of the coordinates. Good. So yeah. So if you do the work, you get something like 4 norm of f is smaller than some variable constant times the expectation of f, or s, sorry, sum over s of expectations over x's of the 2 norm of derivatives. 2 norm to the 4th power, because I applied the recursive inductive hypothesis. And the point is that these derivatives, now you have to look at the definition, but it turns out that the 2 norms of these derivatives are small if you know that f has small restrictions. Okay, so the real question is how to get this thing. Let's talk about that. Okay, so I want to bound the 4 norm to the 4 power. This is just the expectation of f to the 4th by the 2 norm squared again, plus whatever is left. Yeah, so let's say something about how this is obtained. So such bounds were obtained by Bonami and Gross and Beckner, but Bonami actually proved it directly. Gross and Beckner went through some operator stuff. So here is the basic idea from Bonami's proof. If we look at the 2 norm squared of f, for the Boolean cube, it's just f hat s squared, like the squared of the Fourier coefficients, sum over everything. This can be written in a way that's also relevant for the noisy mesh. Just look at f equals s. norm squared sum over all S. So if you look at the two norm squared, then that's just, well, you have to just square that. So it's a sum over all S and all T, or maybe I'll write over T1 and T2 of F equals T1 squared. This is just opening parenthesis. F equals T2 norm to squared, right? So that's the fourth norm. Sorry, that's the fourth power of the second norm. What is the fourth norm of a function? The fourth norm, right? I want to know it because I want to compare these two things. The fourth norm of a function is the expectation of its fourth power. So it's the expectation over x of fx squared. Also known as the second norm squared of f squared. So now I have the second norm squared of something, and I can use the formula from above. So this is just the sum over all S of the equals S part of f squared, two norm squared. This is just completely mechanical. Right. Okay. Now, what is f squared? Let's just write it down. This is sum over S. I have the norm here, 2 squared of the S part of f squared. So f squared is just a sum over T1. Okay, f is just the sum of f equals S over all S. So if I square it, I get all the mixed products. So I get f equals T1 times f equals T2. Okay, and this is just a completely mechanical computation. Now I need to ask myself, okay, if I have a set T1 and I have a set T2, what is the degree as part of this product? Okay, and the answer changes depending on what set I'm looking at. So for the Boolean cube, f equals T1 times f equals T2. This is just, maybe you'll like it better if I write f hat of T1 times f hat of T2. T1 times f hat of T2 of chi of the character of T1 symmetric difference T2. That's what happens when you multiply characters over the Boolean cube. And then what does it contribute to the degree, to the equals S part? Well, it contributes nothing unless T1 symmetric difference with T2 equals S. So for the Boolean cube, this just equals sum over S over sum over T1 symmetric difference T2 equals S of so so you just get the two norm of this, which is f hat T1 f hat T2 squared. Also, you can write it as f equals T1 2 norm squared, f equals T2 2 2 norm squared. Okay, so this was the cube, and now we have two. This is sum over S, sum over T1 and T2, which sum up to S. And now we have this expression for the fourth norm of F squared, and we have this expression for F2 norm to the fourth power. And you just do the computation. It's a computation with numbers. It has nothing to do with operators or functions. You can just show that this is bounded by some constant times F2 squared. So this is the Boolean cube. What? To the yeah. Sorry?
Oh, that will look like you.
Sorry, don't.
9.
9, yes, because I took it to the fourth power, yes. Okay, good. So what? This is the Boolean cube. What happens in the noisy mesh? Well, two things happen. One is that yeah, so you have all these pairs, T1 and T2. Some of these pairs look like in the Boolean cube. Their symmetric difference is equal to S. And from these, it is easy enough to show that if you only look at T1s and T2s such that the symmetric difference is S, yeah, if you look at the 2 norm squared of this, this is bounded by the sum over the same pairs of yeah, and I have the sum over S here, and then you get F equals T1 2 norm squared, F equals T2 2 norm squared to be S. But this is the same thing that we got here. And because of the same number game, this part is bounded by the sum. Okay, so these are, look at these just as numbers. So this is bounded by the sum over S's of F equals S. Yeah, normed squared, which is just the 2 norm squared of F.
This was for mesh?
This is for the mesh, but only when I sum over T1s and T2s that have the same structure as in the Boolean cube. So yeah, and again we have this 9 to the D here. So this is yeah, I already erased what I wanted to get, but I wanted to bound the 4th norm squared of F by this plus some stuff that remains. Okay, so I got this, but I only took into account certain pairs of T1s and T2s. So the question is, okay, yeah, but what happens to the other T1s and T2s? Okay, so which other T1s and T2s contribute to the equals S part? When T1 symmetric difference T2 equals S exactly, it means that T1 covers some part of S, and T2 covers all the rest of S. And on the outside, they maybe contain other things that cancel. if they do not cover all of S, then they will contribute nothing to the degree S part. That's pretty easy to see. So the rest of the stuff that I need to worry about is when T1 and T2 do cover S, yeah, so what if they do cover S, but they cover with overlap? And that's the only part that I need to, that's the only remaining part that I need to bound. Right, so yeah, so, but what I claim is that if I look, yeah, but if I look at the part where T1 and T2, their intersection contains something from S. It's not empty even inside S of the same thing. Okay, my claim is that I can bound it by looking at Laplacians. Sorry, I need. The two norm is not outside. It's this. Yeah. So I see. No, yeah, you're right. It doesn't matter because I'm going to use the triangle inequality, which doesn't hold, but it holds if I add another factor of 9 to the d or something. So yeah, so I'm going to push the norm inside and multiply by 9 to the d, and bound each of these terms, or the sum of these terms, by the sum of the Laplacians t of f. Sorry? Well, okay, I bound it by this. By this. And okay, so why can I do this bound? Because LT of f for t containing S. So now think of t as the intersection of T1 and T2 and S. For this intersection, LT contains all of the f equals T1 and all the f equals T2 for T1 and T2 that contain this T. So yeah, so when I take this Laplacian squared, I get all these terms. Yeah, and that's about it. So I bounded terms that do not intersect in S in one way, and the pairs that do intersect in S, I bounded using the square of the Laplacians, and yeah, and I have yeah, there is a little bit of work, but not much. You get. Yeah, so this is the 2 norm squared of the Laplacian squared when you sum over all S. It turns out to be sum over, yeah. So when you sum up also over S, you get the sum over just all the Laplacians. 4 norm to the 4, and that's it. Main idea.
Any questions for Guy?
First case, the Boolean cube case.
So it's just a computation on. Yeah, I can't find anything now on the board, but you have, yeah, the 4 norms squared, you get it by summing over S, and then summing over the product of the squares of these Fourier coefficients. And if you just compute the 2 norms squared, yeah, what is the difference actually? The difference, yeah, okay, I cannot just do it like formally, but the difference comes from the fact that there are triangle inequalities that you need to use. You get norms of sub-functions, and you want to say that they are bounded. You get the 2 norms squared of a sum of things, and you want to say that this is smaller than the sum of the 2 norms squared of the things inside, and the 2 norms squared does not satisfy the triangle inequality. So you have to multiply by the number of terms that you add. And so you get some exponent in D because the number of terms that appear there depend on the number of ways to partition S into two sets that do not intersect. Yeah, so it's, yeah, so the, yeah, so maybe it's not a 9, maybe it's a 4 to the something. What? No, so it's, I think, okay, I don't remember, but it's some, I think it's, okay, to be honest, 9 to the D is what you get from Beckner's inequality. So I think if you do Bonami's inequality, you get something that more resembles something that you get from counting subsets of S, so more like 2 to the D or 4 to the D or 8 to the D, something like that. I don't remember the details.
You want to get something better than 9 to the D.
Because it's optimal. Okay, so maybe 16 to the D, I don't know.
Yeah.
Something, you get something.
Get the right thing, but it depends on how much. So this was for the mesh. For the other case, that's right.
No, it doesn't reduce to this. It just follows the same scheme. So you need to redefine what Laplacian is. And actually, it turns out to be more tricky than there are multiple ways in which you could define a Laplacian. Because here a Laplacian is just the sum over Ft for T containing S. But if you look at S as a matrix, what does it mean for another matrix to contain the original matrix? Well, there are definitions that you can try, and actually we need more or less all of them. So yeah, so there is the Laplacian, and you have to define the derivative, and the derivative of a derivative here, it's just the derivative. Somehow the derivative of the derivative is just derivative. It all works well, and there when you try to do recursion and you find you have derivatives of derivatives, they don't work so well together, and so you have to write them again as some other like linear combinations of other kinds of derivatives. So yeah, so the scheme is the same, and if you're tenacious, if you go at it enough, you will make it. But everything works a little bit slower.
There'll be another paper of more conceptual.
Yeah, maybe you can even.
The word conceptual is undefined. Any more questions?
Thanks, Tom. I'm wondering for the mesh case, if you make this mesh tighter and tighter, do you get the hypercube result for the continuous hypercube?
I think so, right?
It's tighter. Everything is tight.
Which one?
For the solid cube.
You can get one, yeah, of course.
Right, so there is, yeah, and it's sort of a known technique. It's a B, K, K. If you add enough K's to B. Yeah, okay, yeah. Originally Beckner and also Gross wanted to, so all this discrete stuff, if in the beginning was seen as a way to prove stuff, things on the continuous space. But they looked at the Gaussian space. If you want the solid cube, it can also work, but in a different techniques than what Gross and
yeah, so this notion of a degree for the matrix case, that makes sense because somehow for the Fourier transform of the rank functions, it has to decay with the rank of the frequency. Is that
yeah, right, yeah. So it needs to be it needs to be an invariant space, and it also needs to, and you also need the high degrees to vanish when you apply TG to them, and that will not, it will not work with the usual notion of degree.
Okay, so we're at over time, so let's take any further questions offline and let Frank play again. We'll see you after lunch at 2.